We've looked now at how to translate back and forth from Cartesian to polar coordinates for individual points, but we also want to be able to write equations in polar forms. Just like an equation in rectangular coordinates is a relationship between x and y, a polar equation is the relationship between r and theta. Most polar equations can be written of the form r is equal to some function of theta, where the distance from the origin is expressed just as a function of the angle. So depending on what the angle it is, it tells you how far the radius goes out. We're going to use the tools to translate for coordinate conversions, and typically translating from rectangular to polar is fairly straightforward. We're just going to replace every x with r cosine theta and every y with r sine theta. When we're working to translate in the opposite direction, can get a little more difficult, but we'll look at some examples there as well. Here, if we want to rewrite this rectangular coordinate equation in polar form, where we're just describing that radius in terms of the angle, each x we're going to replace with r cosine theta. So this is r cosine theta squared minus 2 times r cosine theta plus r sine of theta squared. When we multiply out, we get r squared cosine squared theta minus 2r cosine theta plus r squared sine squared theta. If you remember, we can factor out the r squared here, which gives us cosine squared plus sine squared theta minus 2r cosine theta. But hopefully you remember this is indeed 1, so we get r squared minus 2r cosine of theta equals 0. If we're looking to go in the opposite direction, where we want to rewrite this into rectangular form in terms of x and y, sometimes you just have to play with it a little bit. We do know that the relationship of secant we can rewrite as 1 over the cosine of theta. And then when we simplify this, we get 2r cosine theta equals 1. And notice that r cosine theta equals 1/2. But this is indeed x. So we just end up with x is 1/2.